Welcome back. In the last video we have seen that a steady state heat equation, two dimensional steady state heat equation becomes a Laplace equation. So Laplace equation is actually a steady state two dimensional or three dimensional, basically steady state heat equation is a Laplace equation. So that is what we have seen. So we will try to define problems for the Laplace equation. So if you as an application for this heat equation, so you can see if you consider a plate that is heated plate, so initially at some temperature and at the boundary two dimensional. So the boundary terms at the boundary you maintain certain temperature. So if you maintain certain temperature, then actually you can find the temperature of the plate for all times. So that we can solve for all times. So once it reaches the steady state, so we have to find the solution. That means, so you want to see the steady state solution of how the temperature distributes throughout the plate with these boundary conditions. That is to solve a Laplace equation with these boundary conditions. We will see how do we pose this problem as a boundary value problem. So for Laplace equation, we solve the Laplace equation. So we consider first two dimensional, only two dimensional we will solve. So uxx plus uyy equal to 0. So this is xy belongs to some let us consider some domain D. See for not all the domains we can solve this these boundary value problems for the Laplace equation. So we use a separation of variables technique. If you want to use the separation of variables techniques, basically you want to extract a Sturm Liouville problem. So you should have a bounded domain in one direction and bounded you should have a homogeneous boundary conditions at those endpoints. So that means basically your domain should be finite or semi infinite, something like this one. So what we do is we consider this Laplace equation in a bounded domains. For example, rectangular plate. Okay, if we consider this, so you consider the rectangular D is the rectangular plate. Okay, so if you consider this as a D, so rectangle, so you say that this point is 0 0. So 0 0 and this point is 0 to A and this point is 0 to B. So obviously this will be A to B. So this is what is the rectangle plate you have, and here you have this Laplace equation is satisfied here inside this domain, and you have to provide, there is no time, so you have to provide the boundary data on this. So you have to provide the boundary data on this, okay, on this boundary. This is your boundary. So if this is your domain D, the boundary is this boundary, let us call this boundary B. So on this, if you want to give this, so you can provide data everywhere. So all along the boundary you can provide. So here, so if I say this is a Dirichlet problem, so I provide the boundary value problem. So I give you the boundary value problem as so what I provide is I can provide first of all the temperature. So this model says steady state heat equation. So the plate is heated plate is in a steady state. So we want to see how the temperature distribution throughout this plate inside. Okay, once you know the boundary, if you give the boundary, how the temperature varies along the inside the domain. So that is what you want to find. So there is no time. So the boundary value problem is this. So what I do is I try to maintain this boundary at certain temperature, fixed temperatures. For example, U at this is what x equal to, x is varying, x is between 0 to U. So x is actually varying and the y is 0. So you have a 0, ux y equal to 0. Okay, let us say I do not give equal to, so this, let us say f1 of x. Okay, and then here u of x b is actually f2 of x, and here u at now here on this boundary y is varying. So you have x is 0 and y, this you call it g1 of y, and here you provide a data that is u at the temperature x is a and y is varying, so that you give some g2 of y. Okay. If you give like this, so the boundary conditions are basically, so you can write what it is. So u at x0 is f1x, u at x b is f2 of x, u at 0 y equal to g1 of y, u at 0 not 0, this is ay is g2 of y. So, this is what you have. So, where x belongs to, both the cases x belongs to 0 to a, both the cases x belongs to y belongs to 0 to b. These are the intervals. So, if you, how do we solve this boundary value problem? So, the best way is, so main idea is we try to solve by separation of verbs, as we said. To do that, we need to have two opposite boundaries should have 0 boundary conditions. Okay. So, you need 0 boundary conditions, that means you want this either these two are u at u here 0 and here 0, or here 0 and here 0, any one of them. Okay. And then and here you can have both of them non-zero. So, if you want to reduce the calculations involved, what we do is in the here we try to make it 0, both the u at on this boundary we make it 0, and on this boundary we can provide the data, but in that I provide 1 0. Okay. I make this one side 0, other side is function of y. Okay. So, if you do that, because it is a linear problem, linear equation, and you can actually break this problem into 4 types. Okay. 4 problems. So, u1, so break the boundary value problem, the above boundary value problem into 4 new problems. How do we do this? So, I will just graphically I show what it is. So, you have u1, so call this u equal to u1 plus u2 plus u3 plus u4. Okay. And then u1 is satisfying the Laplace equation, u2 is satisfying Laplace equation, u3 is satisfying the Laplace equation in D. Okay. This is actually D, the domain, same domain what we have considered. u4 is also satisfying in this domain D. Only the boundary you have to be careful now. So, now here I get f1 here. So, I make f1 0. So, u is 0 here, u is 0 here. Okay. And here I make u is 0, and here I make u equal to g2. So, I make all these 3 will be 0 and only this one will be non-zero in the first case. Now, what I do is I make this one non-zero, okay. This side is non-zero and here I make it 0. So, that is problem number 2. So, here u0, same u0 is 0, here I make u equal to g1 and here u equal to 0. So, u at ay is 0, u at 0 y is g1, and now similarly here. So, for the problems u1 and u2, 1 2, what you consider is you have the same homogeneous conditions in the opposite side. So, that is at y equal to 0 and y equal to b, and here now you change this, here you make u0 here and u0 here, and here you vary. So, now here I make this f1 and here I make this 0. Similarly, I make this 0 here, I make this here as f2, and here obviously u0 0. So, this is how you break. Then what happens? u1 plus u2 plus u3 plus u4 at this boundary 0, u1 is 0, u2 is 0, u3 is f1, u4 is 0. So, together it is f1. So, that is what is here. Okay. Similarly, here, so in this boundary, here it is g2 0, g2 plus 0 plus 0 plus 0. So, that is g2 what we have. Okay. Similarly, here u3 is, so if you apply here, so 0 0 0 and f2. So, this is what will give you. Similarly, here, so this side you can see that 0 g1 0 0 on this. So, this is how all the boundary conditions are. Now, if you combine them, all these problems together, they still satisfy the Laplace equation because it is a linear equation, and okay. So you break this boundary value problem into 4 new problems u1, you call them u1, u2, u3, u4, and such that they satisfy the Laplace equation. U1 satisfy Laplace equation here, u2 satisfy Laplace equation, u3 satisfy Laplace equation, u4 also satisfying the Laplace equation. And the boundary data you just split it, you just distribute it in some sense, so that boundary is now for u, the boundary is as it is. What if you combine all the data, boundary data for u1, u2, u3, u4 will give you the boundary data for u. And since u1, u2, u3, u4 are satisfying Laplace equation, sum is also satisfying Laplace, that means you got this back u3. Okay. So if you can solve one of these problems, then one problem you solve, and similarly you can work out other problems, so that if you are given any problem like this boundary value problem with the 4 sides are non-zero data, then you can by solving these 4 problems you can give this, and then sum it up, you add all the 4 solutions, that will give you the solution of this boundary value problem. So we will see one. So let us start with u1. So we will take this up for u1, okay, solution method for u1. So we will write this problem for u1 of xy. So let us call this, I do not want to work with u1, let us call this v of xy. Call u1 is as v. So vxx plus vyy equal to 0, xy belongs to the domain, that is a rectangular domain, and v at x0 is 0, v at xb is also 0, and v at 0 y is 0, v at ay equal to ay is g2 of y belongs to 0 to b. So this problem will work out. So we will try to solve this boundary value problem. Okay. So this problem, how do we solve this? So we give the solution by separation of variables. So let the solution be v of xy be x of x, y of y as a non-zero solution. If you look for a non-zero solution for the Laplace equation, then if you substitute this v into the Laplace equation, you get x double dash of x, y of y in the place of vxx plus x of x times y double dash of y equal to 0. Again the same procedure, because this is non-zero you can divide with both sides. So you get x double dash of x by x of x equal to minus y double dash of y divided by y of y. Now you can see that both sides, one side is function of x, other side is function of y, so it should be a constant. So this should be constant, parameters you call this lambda, and so the Laplace equation becomes 2 ordinary differential equations, that is x double dash of x minus lambda x of x equal to 0. Okay, this is one, and other one is y double dash of y and then plus lambda y of y equal to 0. So this has become. Okay. Now if you apply these 0 boundary conditions wherever, this one, okay, vx0 is 0, v boundary conditions first 2, 1 and 2, 1 will give me v at x0 is x of x and y of 0 is 0, implies y of 0 is 0, because x of x cannot be 0, it is a function. If it is 0, then whole thing is 0, v of v0, which is against our assumption that it is non-zero solution. So boundary condition 2 will give me v at xb is 0, that is again x of x, y at b equal to 0, that will give me y at b equal to 0. So this is the problem. So now what you get is boundary conditions, 0 boundary conditions will give you Sturm-Liouville system for y of y. Once you get these eigenvalues and eigenfunctions here, you substitute for eigenvalues for lambda here and try to find the general solution for xn's. Xn's andyn's you combine and put it as Vn, and then take a superposition of Vn's that satisfies the Laplace equation with these two boundary conditions 1 and 2. Apply the boundary conditions 3 and 4 as initial, like we have applied for initial conditions for wave and heat equations. In this method you can get those constants. Okay, that is the procedure. So let us find so let us see what is the Sturm Liouville. So this is the Sturm Liouville problem, obviously regular because it is in the Cartesian coordinates. So you have y double dash y dash 1 into y dash dash plus q is 0 into y equal to minus lambda. Okay, so what we have is minus lambda. So if you do not want minus here, so you can make minus here, so plus here. So here this way also you can make. Okay, before by dividing both sides with this, you can write this way also. By that you can see that this will be plus and this will be minus. So that your Sturm Liouville problem is also is exactly in that form, in the self-adjoint form, as a eigenvalue problem y. Okay, lambda into 1 into y. So lambda into omega is 1 y. Obviously y0 is 0, which is equal to yb. Okay, so this one is already self-adjoint form. W is 1, so the phi psi, the dot product is for the solutions you can define it as, this is what is the domain between. The domain is y is between 0 to b. So the domain is 0 to b, and you have a phi x, or rather because the function of y, let us say phi y psi y bar dy. This is the dot product. So the Sturm Liouville is, so immediately this is a self-adjoint form. So lambda is real, implies lambda is either mu square or lambda is 0 or lambda is minus mu square, with mu is always positive. Okay, and look at all these three cases, lambda equal to mu square. So this will give me, if you consider y double dash minus lambda, so you have y double dash minus mu square y equal to 0. So the general solution of this is y of y is c1 e power mu y plus c2 e power minus mu y. I think earlier also we solved, we see that this is not satisfying. So this lambda is not an eigenvalue. Okay, anyway we can repeat the same. So y0 is 0 will give me c1 equal to minus c2. So your general solution is c1 comes out 2 c1 sin mu y. Now if you apply y at b equal to 0, will give me sin mu v has to be 0. So this will give me sin mu, sorry, this is sin hyperbolic mu b into 2 c1 has to be 0. That implies c1 has to be 0, because sin hyperbolic cannot be 0 for mu is positive, b is positive. So c1 is 0. So implies y of y is completely 0 for every y, belongs to 0 to b. So this implies lambda equal to mu square is not an eigenvalue. The same way you can see that lambda is 0 is also not an eigenvalue. So y double dash lambda is 0, so you have this one. So y of y is actually c1y plus c2. A general solution, y of 0 is 0 will give me c2 is 0. So this has gone. Y at b equal to 0 will give me, now c1b is 0, that gives me c1 has to be 0. So that means this is also gone. So completely 0. So implies lambda equal to 0 is not an eigenvalue. So what you are left with, the third case, that is lambda is minus mu square. So if you do this y double dash plus mu square y equal to 0, y of y is c1 cos mu y plus c2 sin mu y. You apply y is 0 is 0, it will give me c1 is 0 So, this has gone, y at b equal to 0 will give me C2 sin mu b equal to 0, and you want a non-zero solution. C2 is C1 is anyway 0, C2 is you want to be non-zero. So, that sin mu b is 0, that gives me mu as n pi by b. So, n is running from 1 to onwards because mu is always positive. So, your eigenvalues are lambda n's, eigenvalues lambda n equal to n minus n square pi square by b square, n is from 1 to onwards. Okay. And then eigenfunctions are these solutions, sine eigenfunctions call this yn of depends on n. So, I am just labeling as yn as sine. I can take C2 as 1, sine mu is n pi y by b, again n is from 1 to 3 onwards. So, these are eigenfunctions. Now, we consider x double dash minus. So, now we have a plus lambda is this one. So, you have a minus n square pi square by b square. So, because they are depending on n, lambda I am replacing with lambda n. So, I am calling this xn double dash plus lambda, xn double dash plus lambda x of x. So, this is what you have. So, x double dash plus lambda is this, it become minus. So, you have xn of x for this function, this is equal to 0. Now, what is the solution, general solution of this? Xn of x is, so you can call this a n. So, 2 arbitrary constants involved for each n, okay, n is from 1 to 3 onwards. For each n you have a differential equation like this, whose solution is an arbitrary constant for each n, a n, b n's are arbitrary constants, a n e power n pi by b x plus b n e power minus n pi by b x. Okay. This is true for every n 1 to 3 onwards. So, what is your v n of x y, the solution combining, which is the product of, for each n you can multiply x n x with y n y. So, if you do that, you see that a n e power n pi by b x plus b n e power minus n pi by b x into y n is sin n pi y by b. So, this is a solution that satisfies the boundary conditions, 2 boundary conditions 1 and 2. So, you can take a superposition, let this v of x t be this superposition of all this, n is running from 1 to infinity. So, now if you do this, now you apply other 2 boundary conditions to get what is your a n's and b n's. So, other boundary conditions are, what is the other boundary conditions? What you have is just go back and see what is your first problem. So, the problem for other boundary conditions, v 0 y is 0 and v a y is g to y, v 0 y is 0. Now, we apply the boundary condition 3, v 0 y equal to 0. So, this will give me v, it is x y. So, v 0 y is 0 means the left hand side, n is from 1 to infinity, a n, when you put x equal to 0, this simply a n plus b n times sin n pi y by b equal to 0. So, immediately you see that a n's, how do I get this? A n plus b n, a n plus b n is actually, if you take the dot product with the eigenfunctions sin n pi y by b both sides, this side right hand side will be integral 0 to b, this is a function is 0. So, 0 into sin n pi by y by b divided by integral 0. So, integral 0 to b sin square n pi y by b. So, that dy, okay. So, that one if you do this, this will become 0. This is true for every n 1, 2, 3 onwards. So, that means a n equal to minus b n. So, go back and see. So, if you substitute here, so what happens once you know a n equal to b n, you can combine it, n is from 1 to infinity, a n equal to b n or b n equal to a n. So, you can combine a n, b n as minus, so 2 a n, what you get is sine hyperbolic n pi b by x into sine n pi y by b. So, these are your, this is now general solution now. Okay. Now, you apply the other boundary condition 4, that is what you have. So, v at a y equal to 0. Now, for this now your general, this solution becomes this. If you apply, n is from 1 to infinity 2 a n sine hyperbolic n pi a by b into sine n pi y by b equal to g of y. Now, again, so this is a constant, this constant you can get it by applying dot products both sides with the eigenfunctions. So, sine hyperbolic n pi a by b is actually equal to integral 0 to b g of y sine n pi y by b dy divided by integral 0 to b sine square n pi y by b dy. So, this you can see that this will be 1 minus cos 2 n pi y by b. If you apply, you will see that, you can see that it is going to be b by 2. So, it is going to, you can say that this is actually 2 by b integral 0 to b g of y. The denominator I evaluated as b by 2. So, that becomes 2 by b g of y sine n pi y by b dy. Okay. So, this is how you can get your this concept. So, what you need is a n. So, a n's are nothing but 2 goes both sides. So, what you get is 1 divided by b sine hyperbolic n pi a by b as into integral 0 to b g of y sine n pi y by b dy. This is from n is 1, 2, 3 onwards. So, with this a n you put it into here, that is the solution that satisfies now all the boundary condition. So, implies, so you have a, this is the required solution with a n being this, okay, that is the required solution. So, this is how you can solve Laplace equation with this boundary data. So, you need two opposite ends, at least two boundary conditions should be homogeneous, 0 boundary conditions you need. Okay. So, this is how if you solve. So, what you have done is you solved only the problem u1. So, in the same fashion you can solve for u2, apply the same technique u1, u2, u3, u4, you combine them to get the solution for u. This is how you can solve this rectangle problem with Dirichlet boundary conditions. These kind of boundary conditions, when you provide u a temperature at the boundary of the plate, this is called the Dirichlet boundary conditions. Okay, Dirichlet boundary conditions. If you provide this, if you insulate them, that is kind of Neumann. If you provide flux conditions ux, the insulating condition at the boundary, so you get ux or uy depending on the boundary. You say that that is a Neumann conditions. Okay, Neumann boundary condition. So, that is some, for example, normal derivative to the boundary is Neumann. If you provide simply u at the boundary, this is Dirichlet. If you actually combine them, that is Robin type. Robin conditions are combination of them. So, that is dou u by dou n plus u. Okay. So, if you give this Dirichlet boundary conditions, we have solved. We will try to see how we can do with this Neumann boundary conditions. We will not deal with this we will not look into the problems with Robin conditions. Okay. So let us see, let us fix. So maybe we can see. So in the next video, we will try to see. We will try to solve the boundary value problems for the Laplace equation in a rectangular domain with Neumann data on it. Okay. So we will see that in the next video. Thank you very much.